Jamie, there are a couple of questions in the chat box.
Yeah, I'm just reading that one now.
Yeah,
so I see
so let
James.
Yeah, I could read them out for you if it makes it helpful.
No, I don't mind reading them.
Okay.
Or yeah, so James Duff is asking, what type of foot squared is typical for a deep geothermal suitable for an ice rink? That's, again, as I said before, it's going to depend on the ice rink. It's going to depend on your schedules. It's going to depend, as I said on that other slide, it's the peak load, the monthly load during that peak month that leads up to the peak load, and then your annual energy balance. All of these are going to be systems building specific, and they're going to play into how large of a bore field you're going to need. So it's not a clear answer, but there are, if you knew the hourly demands that you would want this ground source heat pump to meet, you could go and calculate what the expected ground loop would be.
Right, with presumably why you want to also get your rink to be as efficient as it can be operationally now. So
Correct.
Okay.
Yeah.
Another question.
And again,
sorry,
this isn't just going to be the straight up heating and cooling loads of the building that you would input into this calculation. It's what you want the ground to meet. So if you have energy recovery where you take heat from your ice pad and use that to offset heating loads, then you know that the amount that the ground would need to make up for is going to be reduced. So again, it's really important to look at the overall energy balance of the system. And then from there, you can determine what the ground needs to do. And then you can go and size the ground. And the key here is you want to minimize that size of the ground. Because as I said before, it's about, I think I said $4,400 per ton. So these are expensive, but they're inexpensive to operate. So again, it's not the most straightforward answer, but hope that clarifies it a little bit.
There's a question too about if you've seen shallow geothermal design as opposed to deep geothermal design.
There are some. So there are some where you go shallow. Again, this is not in an ice rink context that I've seen it, but there are some situations where you're not going vertical, you're going with those horizontal boreholes. It's more of a slinky design. So there's just coils that are wrapped around horizontally, and it kind of looks like a slinky that someone just put on the ground and spread out. And then, it all depends on site conditions and what's available. But they do exist.
Okay, great.
So James had a follow-up comment, which he said, our rinks are fairly similar in design and energy consumption. So that's good. That means that once you go through the analysis for one rink, there would be only minor variation rink to rink, which would simplify the analysis once you get that first rink complete, but you still do need to go through the first rink. And no problem, James.
Great, thank you. So I don't see any open questions. We've set aside about 20 minutes for Q&A. So if you have any additional questions, now would be the time while we have our technical experts here ready and waiting to answer them. And I do see a question that's come up here. What are the good and bad if Simcoe refrigeration system is controlled by the whole building BAS system? Is that what the experts are recommending?
I can answer that one. So I'm just to clarify the question, when they're talking about Simcoe refrigeration system, I hope that you don't mean that the customer is tying within Simcoe for the BAS system. I think it's more open, saying that you need a control system, excuse me, for the refrigeration system, and you need a control system for the building. So we've done many projects and we have seen the good and the bad. So the bad that we have seen is when there's two different control systems. And just to give a very simple example, a refrigeration plant is running, building don't need heat, so the heat is dissipated outside, it's wasted. Refrigeration plant is not running, building is calling for heat, and again, it's like the boiler is going to start up because the two systems do not talk together. So I would say the best scenario is not necessarily a Simcoe BAS system, but it's a system which is handling both the refrigeration and the building. and both communicate, meaning that when the building is calling for heat, we need to run the plant. And if the building is not calling for heat, we don't need to run the plant. So basically, it's really having communication between both systems. So I hope I answered the question.
Yeah, Benoit, if I can add to that, it's a great answer. So far, based on our site walkthroughs, what we think currently will work best is that Simcoe's system can easily be integrated into the building automation system, which typically would read a lot of the good information that Simcoe's trend logging and monitoring. So currently the thinking is that again, Simcoe's so far the controller we think is a good controller that optimizes the more sophisticated operation of the refrigeration plant. But as Benoit said, is that a lot of that information can be communicated to the building automation system. So for the rest of the facility, that can again integrate the two, saying when heating is required, the refrigeration plant's doing the right thing to actually use that heat in the facility and vice versa, right? So that's kind of where we're thinking. Again, it's not a we don't envision a Simcoe control system for the whole building. We envision an integration between them, where typically a BAS system will just overlay and monitor the information from Simcoe and maybe give it some simple commands that Simcoe's controller or another refrigeration system controller can actually control the refrigeration plant, because a little bit more sophistication involved in that. Hope that helps.
So there's another question on what compressor improvements or efficiencies are being applied. So there's constant development from compressor manufacturer trying to improve their efficiency, but mechanical equipment is a mechanical equipment. So we're seeing slight improvement on piston compressor from some manufacturing being anywhere between 5 to 10% more efficient. There's a lot of development on screw compressor as well, but what we're going to see is not necessarily improving on the compressor itself, but it's reducing maintenance requirement and changing some of those parts, which could have a tremendous impact on the maintenance cost of the overall rink operation. The other thing that we see is on the heat exchanger, moving from some type of shell and tube equipment to plate and frame equipment, for example, where we can tighten the temperature difference between the operating fluid, whether it's ammonia with glycol, ammonia to brine, or CO2 to brine, or some stuff like that. When we're tightening those temperature difference, we are strongly improving the COP of the overall system. And this is what we're trying to achieve.
I think the next question from Stephen Hamilton looks like it's for me. Stephen asks, using rooftops for solar panels as a renewable offset. If not using a roof, how practical is a parking lot shelter to use as a renewable offset? It's going to depend on the available mounting area, and then the orientation and the shading and the angle that you can mount the panel. So there's no real difference between a parking lot shelter or a rooftop. One good thing typically about a parking lot shelter compared to a rooftop is there's not a bunch of mechanical equipment that you also want to put there. So when you put a bunch of things on the roof of a building, you have exhaust penetrations that you need to start worrying about. You have structural loads within the building that you also need to start worrying about. You have the roof of the building itself that maybe it's really near the end of its life. So now you're forced to refurbish the roof and then install these, and it becomes more expensive. So there's a lot of practical considerations when you compare the two, but in terms of a generation perspective, if the area that's available is the same, if the shading factors are the same, if the orientation is the same, it wouldn't really make a difference.
So I can see that James have two questions. Are there companies other than Simcoe that can provide the controlling strategy? Of course, James, any control company can look at the entire operation and provide a system that will take care of what's the requirement. And your second question is it better like recip compressor or screw compressor for ice rink refrigeration system? There's various approach to that. I would say it could be personal choices, but mechanically speaking, both of them will do the same thing. Piston compressor have a slightly lower energy consumption than a screw compressor, although piston compressor needs to have regular overhauls every 5,000, 10,000 hours, 15,000 hours, while screw compressors could run for 40,000 hours, 50,000 hours before overhauls. So if you compound those two factor into the equation, you know, energy consumption on one side and maintenance and overall, you know, cost on the other side, at the end of the day, I personally believe that the screw compressor is a better approach, especially that there's a lot of manufacturers which are actually building, I would say, light industrial compressor instead of the big heavy industrial machine that we see in industrial refrigeration. And also there's a lot of new development, and we can even start to see semi-hermetic ammonia compressor on the industry instead of having open ammonia compressors. So that would be a dramatically change into changing shaft seals and even the risk of having some ammonia leaks from the open drive compressors. So this is where the trend is going. This is where the market is going.
All right. I think Stephanie's question is for me, but it's pretty general. Given the long paybacks for these types of interventions, what approaches are being used to make these projects financially viable? On the whole, that's a very difficult question to answer, at least from my perspective. I think the first step is trying to figure out what the lowest hanging fruit is. As we said before, it's first, you know, reduce loads, energy recovery, renewables, and you go through that list and you start to identify, you know, you need to check the system. So we have there's industry experience, for example, in this expert panel that they've went and worked with a bunch of systems, and these systems have different performance levels, and you can try to develop on a subconscious or on a highly detailed statistical level, somewhere in between there even, you can start to get an understanding of which systems apply best in which situations. And then from there, you can start to use these to start guiding the analysis that you would then do in individual buildings and in different locations to start checking which ones are the most viable. Moving to you know, a zero carbon future, it's still something that we still need to learn to understand, but it's an important step given the motivations based upon climate change that we need to reduce our impacts on the planet. And going through the process is just part of the journey that we are going to have to go through. You know, before there were boilers, they didn't know how to heat places. You know, they were burning wood. It's the same concept that you need to start checking and using knowledge and trying to make the best decisions that you can based on the situation. So it's not exactly the most direct, like most of my answers, I guess. It's not the most direct or straightforward answer, but it's just, that's the process that has to be followed. It looks like Frank wants to say something.
Yeah, no, just I wanted to talk more about, I guess it's probably Mario's question. It might be related to Stephanie's question, I guess. For Mario's question about when calculating payback, why is the capital cost of a component not factored in your calculations, especially given that the equipment is tending to fail before it's anticipated end of life? So there may be some miscommunication on my side, but we do, in the life cycle costing analysis that we will perform, we will be taking into consideration capital life. It was actually, you'll see in the last two slides of the heat pump analysis, it took the cost implications of going to a gas-fired boiler system as well as electric boiler. So the fact is, once a piece of equipment is either end of life or needs to be replaced, that is a trigger event. And so what are the options that you do with afterwards? So we'll look at all options, including capital cost and maintenance costs, as Benoit mentioned as well, in terms of the compressors, for instance. So you need to take maintenance into consideration. You just need to take utility costs into consideration. But definitely capital costs will be a part of that, as well as, again, this, as Jamie mentioned too, this is kind of a bit of a newer territory for the approach that, based on the approaches that have been taken in the past. A lot of things have been focused on energy conservation, but now the low carbon world, low carbon approach is very different than just energy efficiency, because typically the approach for low carbon is to go to electrification, which costs a lot more than natural gas. At least today it does, anyways. And so that's sort of a different approach than typically energy conservation would do. But that's real life. That's what we're up against. And in terms about, you know, financially making things financially viable, we're going to find out soon. We don't have all the answers. We're going to find out, which was kind of an interesting observation too, with the heat pump. The heat pump alone in itself is not a very very attractive financial option, but it's going to depend on a few factors. First of all, you know, the capital cost of the heat pump or heat recovery chiller, as well as what's the price of carbon? What's the alternative to reaching the carbon goals? What's the alternative? And those will be explored a little bit further. Hopefully that helps out a little bit more. Oh, then there's another question, I guess, regarding some metering. Yes, so what we envision for the pilot, anyways, and is that we'll be doing, we're looking at monitoring, yes, the refrigeration plant in terms of energy uses. We're at this point in time, we're trying to get as much trend information as possible to facilitate getting, you know, energy usage. We will be adding likely CT sensors. So to them, just to follow up, but not sure if that will be done for every single facility because of the implications of getting that done. But we're sort of at that stage now where we're trying to determine what we have in the trend log information, and then filling in that gap of trying to understand what the energy is used. If it can't be determined through the trend logs, we'll be looking at that for at least the archetypal facility, and maybe a handful of others where that is an important factor, a critical factor. Mm-hmm.
Okay, I can take the next question on CO2. Actually, what we're seeing on the market is actually not a pushback, but it's more interest into replacing system with CO2 system. So if I take an example in Quebec, 80% of the R22 system that has been replaced were with CO2 systems. So just to put things in perspective, nothing is perfect. No refrigerant has the perfect solution. So if we take synthetic refrigerant, they have a strong impact on the global warming potential, and they're not the right solution in terms of environment. If we take ammonia, it's a perfect refrigerant. It's natural refrigerant. No involvement in global warming and environmental issue, but it's a B2 refrigerant, meaning that it's toxic and it's flammable as well. So we need some construction on mechanical room that needs to take care of that aspect. When we move to CO2, it's an A1 refrigerant, meaning that it's non-toxic, non-flammable. It's comparable to R22, for example. But the only thing is we have to deal with higher pressure. So there's no requirement for heavier wall construction. Actually, CO2 systems are smaller in terms of size than ammonia system. We put everything that we can do to manage the safety issue regarding high pressure. So we're using high pressure stainless steel piping. Everything will be welded according to very specialized welding procedures. All the relief pipes are piped to the outside. And actually in Canada, because of the special nature of CO2, when we are using this type of system in the Canadian environment, we actually end up having a system with a better COP and with lower energy consumption. And again, it's an A1 refrigerant, so we don't even need a vestibule. In terms of if we ever have a release of CO2 into the mechanical room, this is the refrigerant that can have the highest concentration of refrigerant into the mechanical room. We're good all the way up to 50,000 ppm before affecting the health and the safety of the people inside. any other refrigerant, any other synthetic is about 1,000 ppm. And when we're talking about ammonia, we're talking about 35 ppm. So that gives you an idea that CO2, yes, it does have higher pressure, but everything is put in place to make sure that this will not create a safety issue.
Ben, well, there might be a question about electric dehumidifiers too. Question: can a single dehumidifier generate the same amount of tons as a gas-fired desiccant?
Yeah, that's a pretty good question. The electric desiccants are available in smaller model, because at some point when we have higher, I would say bigger amphitheater, like I don't know, with 10,000 people, 15,000 people, the requirement in terms of dehumidifier will greatly steer toward using gas-fired desiccant instead of electrical. And it's only a question of what is the size of the electrical entry and what will be the requirement of amperage and stuff like that. So they are available in smaller size. In some gap, we have both available, gas-fired and electrical. And when we get into the bigger size, it will be gas-fired desiccant. So there's another question on CO2 system. Yes, CO2 system does use higher pressure than ammonia. So typically on the low side, we will be around 400 PSI, and on the high side, we will be around 1200 PSI. So, and an ammonia system will be about 30 to 40 PSI on the low side, and maybe all the way up to 200 PSI on the high side.
Okay, it looks like we don't have any open questions left. I guess we maybe got one more minute if anyone has a last minute question they want to throw in there. Okay. And I don't see any in the chat box either. So that's great. Well, thank you everyone for your questions and your answers. I think everybody learned quite a lot. I know it was a lot of technical details, but hopefully slowly everyone's coming up to speed.